Hi, this is Eric with Math from the Gut, and welcome to part 3 of test driving the Pythagorean Theorem. Here, we are going to take our first test drive as we consider degenerate cases. In this case, degenerate refers to the triangle collapsing into a simpler object like a line or a point. But first, let's discuss how we'll tackle each of our test drives. In general, we'll start by considering what common sense tells us. Next, we'll try out some numbers and see if they match our common sense. Then, we'll consider other possible formulas for the Pythagorean theorem and show that they don't work since they fail the common sense test. And finally, we'll show that the Pythagorean theorem behaves as expected in all cases. This usually requires some algebra, so you'll see x's and y's instead of numbers. Give this a try, but if you have trouble understanding it, just skip over it. You know, a lot can be learned without algebra, just by using numbers. In fact, I spend a lot of time just playing around with numbers to get the feel of a new equation. As appropriate, we'll skip some of these things for some of our test drives. So, for our first test case, let's consider what happens as the y leg vanishes while the x leg stays the same. We'll mark the original hypotenuse h1 and keep track of it, like this. Now, we'll let the y leg vanish like this. Notice how doing this forces our hypotenuse length to change from h1 to h2. What happens to the length of the hypotenuse when the triangle collapses like this? How does h1 compare to h2, our final value of h? Here, we'll do it again. Hopefully, you can see that the hypotenuse and the x-line are now exactly the same. The triangle has collapsed into a simple one-dimensional line, and the length of that line is simply x. The arrow that I use here just represents the idea that h, the length of the hypotenuse, gets closer and closer to x as y collapses to 0. Hopefully you can see that that happens. When y actually equals 0, like what we see here, then h exactly equals x. We'll visit this in more detail soon. The next case is the same idea. Here, the x length goes to 0 instead, like this. What is h when x is 0 and the collapse is complete? Hopefully, you can see that h equals y. And finally, what happens to h when both the x and y legs vanish together, like this? Hopefully you can see that there is nothing left after this collapse except for a point. And how long is a point? Well, a point is actually zero-dimensional. It has neither length nor height. So its length is 0. Hopefully these results all make sense. Now, let's see if the math lines up with this. So, what happens with our math as the y leg gradually vanishes? We'll start with our trusty 3, 4, 5 right triangle. Remember that the Pythagorean theorem tells us that h equals the square root of x squared plus y squared. So, like we discussed in part 2, this becomes the square root of 4 squared plus 3 squared, or the square root of 16 plus 9, which is the square root of 25, which equals 5. Next, let's reduce y from 3 to 2, like this, and see what the Pythagorean theorem tells us. Applying the new numbers, we see that h now equals the square root of 16 plus 4, or the square root of 20, which is about 4.5. The squiggly lines here mean that the answer isn't exactly 4.5. We're just saying that 4.5 is close. Now, we collapse y further from 2 to 1 as follows. This time, h is the square root of 16 plus 1, or the square root of 17, which is about 4.1. You can already see that as the y leg gets small, the hypotenuse is already getting quite close to the length of the x leg. In other words, 4.1 isn't that far off from 4. Okay, Let's complete the collapse and let y equal 0. This is the big test. Let's see if the hypotenuse equals 4 now. Doing the math, we have h equaling the square root of 4 squared plus 0 squared, which is the square root of 16 plus 0, or the square root of 16, which exactly equals 4. We can now see that when x equals 4, h gets closer and closer to 4 as y shrinks. When y has completely collapsed, h exactly equals 4. So, the Pythagorean theorem seems to pass this test quite nicely. Now, let's think for a minute about why this degenerate case works. What are we doing? Okay, the first thing we do is take 4, square it, and add 0 to it. Adding 0 does nothing, so we're really just squaring 4. So we start with 4, and then we square it to get 16. What's the final step? We just take the square root of 16 and get back the 4 we started with. So we start with a 4 and end with a 4. Why does that happen? This happens because squaring and square rooting are inverse operations. One undoes the other. Think of 4 as the length of a square. When we square 4, we get an area of 16. Then, when we take the square root, we ask, what length gives us an area of 16? And guess what? It's just the length of 4 that we started with. It's a long story that ends up right back where we started. This is quite a mouthful, so you might want to think about it a bit on your own. We're basically going from a length to an area back to the length again. An easier example of inverse operations would be adding 1 and subtracting 1 from a number. Subtracting 1 undoes or cancels out adding 1. It's like somebody gives you something, so you now have 1 more, and then somebody else takes it away. So you're left right back where you started. Thus, we can say that adding 1 and subtracting 1 are also inverse operations. One undoes the other. Going back to the original slide, we also see that the number under the square root gets closer and closer to 16 as y shrinks. Notice how we first add 9 to 16. Then 4, then only 1. And finally we're adding nothing at all. Notice that as this happens, as the number we're square rooting gets closer to 16, our square root result must also get closer to 4. You can also think about the square here. As its area gets closer to 16, the length of its leg, in other words the square root of the area, must also get closer to 4. We see that exactly the same kind of thing happens when x vanishes instead of y. Again, we start with our 3, 4, 5 triangle and our equation for that triangle. This time, though, I'm going to collapse it in one step, like this. Hopefully you can see what is going to happen. Since x is now 0, the Pythagorean theorem tells us that h is equal to the square root of 0 squared plus 3 squared, which is the square root of 0 plus 9, or the square root of 9, which is 3. This shows us that h equals our y value of 3, as we expect it should when our x length has vanished. Now, let's see what happens if both x and y collapse to a 0 length at the same time. We start again with our 3, 4, 5 right triangle and our formula for that. This time, we collapse both x and y together, like this. Our triangle is now degenerate in both directions and is just a point. Since x and y both equal 0 now, we have h equaling the square root of 0 squared plus 0 squared, which is the square root of 0 plus 0, or the square root of 0, which is 0. Everything is 0 here. This indeed matches our intuition for what we felt should happen earlier. Let's see how this test drive can prevent us from using a wrong formula. Let's say that we're having a really bad day and we had the Pythagorean theorem all jumbled up with other formulas in our head. Let's say that we're taking a test and we think that the formula might be the square root of pi times x squared plus pi times y squared. Notice that pi is this symbol over here. If you don't know what it is, don't worry. Just think of it as a number that is close to 3. So what do? Let's try a simple degenerate drive test. We'll let the x leg have a length of 1 and the y leg be completely collapsed with a length of 0. Common sense tells us that this is just a collapsed triangle. In other words, a line whose hypotenuse equals 1. Note that this symbol means suggests or implies. So we're saying here that having x equal 1 and y equals 0 means that h equals 1. In other words, the hypotenuse line and the x-line are exactly the same thing. Well, does this formula give us an answer of 1? Let's see. Using this formula, we have h equaling the square root of pi times 1 squared plus pi times 0 squared. Since 1 squared equals 1, this becomes the square root of 1 times pi plus 0 times pi, which equals the square root of pi plus 0, which is just the square root of pi. But the square root of pi, the number that multiplied by itself is around 3, clearly is not 1. We can therefore see that we better not trust this formula. It clearly doesn't work. We can even see that any number other than 1 in front of x squared or y squared will give a bad result. Throughout this entire test drive, note how much we did without having to compute things exactly. For example, we didn't need to know what the square root of pi equaled in order to tell that something was wrong. Having a good feeling for what is going on often tells us much more than simply calculating precise answers. In fact, it's what makes us different than machines. So, let's try one more formula. Here, we're adding 1 to our usual Pythagorean theorem. Let's see what happens when both x and y equal 0. And our triangle collapses to a point. In that case, we expect h to equal 0 since a point has no length. But when we plug 0 in for x and y in this formula, we see that h equals 1 plus the square root of 0 squared plus 0 squared, which equals 1. This result is clearly not the 0 length that we expected. So we're correct in deciding that this is just another bad formula. Now, how did I know to try this degenerate case to show that this was a bad formula? It really comes from the experience of thinking hard about so many equations, but I'll try to let you inside my mind here. When I see this formula, I immediately notice that it never allows h to be less than 1. This is because the square root of a number, think length of a square, can never be less than 0. So this part is never negative. We're always adding 1 to some number that must be 0 or greater, and the result therefore must be at least equal to 1. So, all I need to do is pick a degenerate triangle whose hypotenuse is known to be less than 1, and then show that this formula doesn't produce the small h that's required. Hopefully, you can see that adding any number other than 0 to the Pythagorean theorem gives us a similar problem. Let's now discuss degenerate cases in general by using some algebra. We start off with our general equation. Now, for the degenerate case where x collapses to 0, we have a vertical line. Here, the hypotenuse length becomes equal to the square root of 0 squared plus y squared, or the square root of y squared. The square root of y squared. This means that we first square y and then take its square root. Remember now that squaring and square rooting are inverse operations that undo each other. This means that the square root of y squared always equals y, regardless of what number y happens to be. Using our square analogy, we start off with the square of length y. We then square that length to get an area of y squared, and then take the square root of that area to get back our length of y. So this completely works in the general case as expected. The same type of thing happens when y collapses to 0 and we have a horizontal line instead. And finally, when x and y both go to 0, h equals the square root of 0 squared plus 0 squared, which is the square root of 0, or 0 as expected. So the Pythagorean theorem jives with our intuition about degenerate cases in a general way. I'm hoping you can follow most of that even if you haven't learned algebra. One huge idea in the math from the gut way of thinking is to try and see things in as direct and simple a way as possible. I really don't like things that require a lot of separate steps to understand. After this test drive, I'm hoping that you can now look at the Pythagorean theorem and very quickly, almost immediately, see that these degenerate cases work as expected. If not, please spend a little more time going over it until you can. It's one thing to follow things step by step, but it's quite another to be able to see the whole thing almost at once on your own. Okay, so in part 4 we'll explore symmetry and how the Pythagorean theorem treats x and y in the same way. Again, please leave comments. It can get very lonely here. See you in part 4.